Uh, Good morning, everyone, and welcome to this session. Yesterday, during RSC lecture, we had seen uh, a differentiation between heat engine, refrigerator, and heat pump. Okay, or we can consider refrigerator or air conditioner as one application when we are considering COP. So we had gone through the derivation of the formulas and derived the COP of refrigerator or air conditioner, and we have also derived the COP of heat pump. Okay, so today we will see what is the Carnot refrigerator and how can we calculate Carnot COP. Again, this will be revision from thermodynamics. After that, we will see uh, some questions related to Carnot COP. We'll solve a numerical related to Carnot COP. After that, we will see definition of 1 ton of refrigeration, and if time permits we will start with star label. So we have already seen this relation. COP of heat pump is equal to 1 plus COP of refrigerator. So this relation is important. You have to remember this relation. So in thermodynamics you had seen Carnot engine, and in case of engine we had four processes, and based on that we got the efficiency of Carnot engine in terms of temperature only. Okay, so this was the formula. So for in case of engine, efficiency is T high minus T low upon T high. So uh, one more important point to note here was Carnot's, in case of Carnot cycle, the efficiency of Carnot cycle, I'm talking about the engine, not Carnot refrigerator, it depends on two temperature limits only, T high and T low, and not on the nature or amount of working substance. So this you had seen in thermodynamics. Now, uh, Carnot cycle is impractical. There are many reasons. First reason is because it is impossible to perform frictionless process. So if you see Carnot cycle, we have isothermal heat addition from 1 to 2. This is about Carnot heat engine. So 1 to 2 is isothermal heat addition, 2 to 3 is isentropic expansion, 3 to 4 is isothermal heat rejection, and 4 to 1 is isentropic compression. So in this cycle, if you see, all the lines are solid lines, meaning the cycle is reversible cycle. Okay, so here one reason why this Carnot cycle is impractical is because it is impossible to perform frictionless process. Therefore, isentropic expansion and isentropic compression, okay, these are not possible. Then again, if you see over here, process 1 to 2, this is isothermal heat addition. So you cannot add heat at constant temperature. Okay, theoretically you can add, but practically it is not possible to add. It is impossible to transfer heat without temperature difference. So that is why isothermal heat addition during process 1 to 2 and isothermal heat rejection during process 3 to 4, it is not possible. Also, you should note that isothermal, in case of isothermal process, piston should move very slowly. Okay, then only inside the temperature will remain same. Okay, if piston moves slow, and during isentropic process, isentropic means it will be reversible and adiabatic. So there in that case, heat transfer should be zero. So piston should move very fast. So during one cycle itself, uh, for some part the piston is moving slow, very slow, and then piston is moving very fast. This is not possible. That is why we say that Carnot cycle is impractical. So this is about Carnot heat engine. Now we'll see what do you mean by reversed Carnot cycle. Okay, so in case of reverse Carnot cycle, what we will do is Since this is a these all the four processes are reversible processes, we are reversing the arrows. So left side you can see Carnot cycle, which is power producing cycle, a Carnot heat engine, and right side you can see reverse Carnot cycle, which is power consuming cycle. So here you should note one thing, that on PV diagram, if arrows are in clockwise direction or on TH diagram as well, so the cycle is power producing cycle. And on the right side, if you see PV and TH diagram, arrows are in anti-clockwise direction. So whenever you find arrows on PV and TH diagram in anti-clockwise direction, it is power consuming cycle. So coming to this one, reversed Carnot cycle, or you can call this as Carnot refrigerator or Carnot air conditioner. So in this case, we have process 1 to 2 isentropic compression, then process 2 to 3 is isothermal heat rejection, then process 3 to 4 is isentropic expansion, and process 4 to 1 is isothermal heat absorption. So this is we have plotted on PV diagram, and similarly on TH diagram it has been shown. Okay, so the only difference which you have to remember over here is Carnot heat engine, it is in clockwise direction, the cycle is in clockwise direction, and reversed Carnot cycle, which is power consuming cycle, either refrigerator or air conditioner, or you can say heat pump. In that case, the cycle is anti-clockwise. Okay, so here you can see I have written the three devices. First one is heat engine, second one is refrigerator, and third one is heat pump. So according to the derivation, the actual efficiency has been written over here. Actual COP is also written over here. So actual COP for refrigerator will not see for heat engine, will see only for refrigerator and heat pump. So actual COP of refrigerator, we had already derived this, it is Q2 upon Q1 minus Q2. Now you should remember that we can change the notation. Okay, just in case of refrigerator, the upper reservoir is higher temperature reservoir, lower reservoir is low temperature reservoir, and you can name this as either Q1 or QH, and the lower one as Q2 or QL. Now, in order to get the Carnot COP, what you have to do is you have to just replace Q by T. Okay, so you can see the formula over here. Carnot COP for refrigerator, it is T low upon T high minus T low. And if you consider heat pump, COP is what is the desired effect in case of heat pump? It is heating effect. So it will be Q1. Q1 is the amount of heat being supplied to this TH reservoir, which is house. If you consider home heating is the application of heat pump. So in that case, what will be COP? Desired effect is Q1 upon work supplied Q1 minus Q2. Similarly, when you are writing Carnot COP of heat pump, you have to just replace this Q by temperature. So for Q1 corresponding to Q1, what is the temperature? TH. So TH upon TH minus TL. So like this, you have to remember the formula. So we'll see this now. What do you mean by, what does a ton mean? Okay, so now here you have to just see the different spellings of ton. Okay, so this spelling is TON. So ton is a unit of weight. Okay, now there are three different types of tons. So you should be clear with this. So here you can see this diagram. First one is 1 US ton. It is also known as short ton. Then 1 ton, see this spelling, TONNE. So 1 TONNE, this 1 ton is known as metric ton. And there is one more ton which is known as British ton. So 1 British ton, it is known as long ton. Okay, so when you are talking about 1 ton of refrigeration, you should be clear that out of this 3 tonnage, which ton we are talking about. Okay, so one by one we will see what is the difference between these three tons: a short ton, metric ton, and long ton. So first we will see. So the American ton, okay, US ton. it is also known as short ton. So let me show this. So American ton, it is also known as short ton, and it is equal to 2000 US pound. Okay, then if you see the second ton, TONNE, it is also known as metric ton, and this ton usually we use in our regular calculation, which is equal to, this 1 ton is equal to 1000 kg, kilogram, or it is equal to 2204.6 pound. So this ton, metric ton, it is larger than US ton. Okay, next type of ton is called British ton. Okay, so next type of ton is called British ton. So here you can see British ton, it is also known as long ton, and one long ton is equal to 2240 pounds. Okay, so this is the difference between the three tons. So which ton we are using in refrigeration and air conditioning? So when we say 1 ton of refrigerator, we have AC of 1 TR. We have to actually know what is the meaning of that. So we'll see in case of refrigeration and air conditioning, what is the definition of 1 ton of refrigeration. Okay, very important definition. Please understand this. So I'll be reading the definition side by side. You have to see this diagram. So 1 ton of refrigeration is defined as amount of refrigeration effect produced by uniform melting of 1 ton. Okay, now here you can see this diagram over here. So here ice is kept, okay, and this ice is 1 ton. Okay, now this is not equal to 1000 kg. Okay, it is equal to 907.185 kg. Okay, so this you have to remember that it is short ton. So we are using 1 US ton short ton. So 1 US ton is equal to 907.185 kg. So that is why we'll see again this definition. 1 ton of refrigeration is defined as amount of refrigeration effect produced by uniform melting of 1 ton of ice. So this ice is kept, suppose this ice is kept in a box. Okay, so because of the since the surrounding is at higher temperature, what will happen? This ice will melt, and the ice will melt and it will get converted into water. So by uniform melting of 1 ton of ice from and at 0 degree Celsius, so ice will be at 0 degree Celsius, and it will melt and it will become water at 0 degree Celsius. So you should understand that there is only latent heat involved over here. So uniform melting of 1 ton of ice from and at 0 degree Celsius in 24 hours. Okay, so I hope the definition is clear. So suppose you are considering a cabinet, and in that cabinet you are keeping 1 ton of ice. Okay, now 1 ton of ice is short ton, 907.185 kg. Okay, now what will happen? It will, the ice will absorb latent heat from the surrounding, and it will melt and it will become water, which will again be at 0 degree Celsius. Okay, in 24 hours. That is known as what? 1 ton of refrigeration. Now latent heat of ice is 335 kilojoule per kg. So we can now calculate what is the value of 1 ton of refrigeration. So 1 ton of refrigeration is equal to, what is the mass of ice? Mass of ice is 907.185 kg, which is short ton, multiplied by latent heat. So here what we are calculating is this part. This part is mass into HFG. Mass into HFG. Now mass of ice is 907.185, and HFG is 335 kilojoule per kg for ice. So this will give the latent heat part divided by, now what is the time? 24 hours. Okay, so 24 hours we have to convert in seconds. So 24 into 3600. So if you calculate this value, you will get 1 TR is equal to 3.5 kilojoule per second. So what is meaning of this? Suppose we have a room, okay, and you are installing over here 1 TR air conditioner, 1 TR air conditioner. So this is known as capacity. Okay, capacity is denoted in TR, tons of refrigeration. So suppose this is a room, and in that room we are connecting 1 TR of AC. Okay, so what is the meaning of that 1 TR? It is removing 3.5 kilojoule per second of heat from the room. Okay, 3.5 kilojoule per second heat is removed from the room. This is meaning of 1 ton of refrigeration. Now, for numericals, we might require some other unit of 1 TR as well. Okay, so we'll see what are the different units. So 1 TR is 3.5 kilojoule per second, a very important relation. This will be used throughout the subject to convert the heat into whatever heat is removed from by the application. Suppose we are using refrigerator or air conditioner, the capacity we have to always calculate in TR. So this 3.5 value we will be always using in the numericals. So now suppose you want to convert this 3.5 kilojoule per second into kilojoule per minute. So you have to multiply by 60. So 3.5 into 60 will give you 210 kilojoule per minute. So 1 TR is 3.5 kilojoule per second, or 1 TR is 210 kilojoule per minute. Here you should remember some other units of ton of refrigeration as well. Usually these units are asked by industries. If the industry is recruiting you in HVAC field, heating, ventilation and air conditioning field, in that case, usually the what is the meaning of 1 ton of refrigeration? Okay, they ask, and you should remember this different units of that. So 1 ton of refrigeration, 1 TR is 3.5 kilojoule per second or kilowatt. That we have already seen the derivation. Okay, so this derivation we have already seen, 3.5 kilowatt or kilojoule per second. Okay, so if you multiply this by 1000, you will get in watts. So 3516 watt. Okay, then the unit of the value of 1 ton of refrigeration is also equal to 3000 kilocalorie per hour. The next value is 1 ton of refrigeration is 12,000 BTU per hour. BTU is British thermal unit. Okay, now this value is, you will find this value if you have air conditioner. Indoor unit is there. So if you check the indoor unit now, and if your air conditioner is of 1 ton, you will find that it is written over there, air conditioner is of 1 ton and 12,000 BTU per hour. Okay, if you have air conditioner, you can locate this. Then after that, 1 TR is also equal to 12,660 kilojoule per hour. So this is one more unit, and also 1 TR is equal to 4.7 HP. So these are the different conversions of 1 TR of 1 ton of refrigeration. So now we will be understanding few concepts related to this Carnot COP. So when we are looking at this now, these questions which I'm about to ask, it is only related to this one, refrigerator. Okay, so my first question is, if you are using a refrigerator or air conditioner in summer season or winter season, in which season do you think COP will be higher? Okay, so to answer this question, what we have to basically see is Carnot COP formula. So what is Carnot COP of refrigerator? It is T low upon T high minus T low. So from this formula you can clearly see that if T low is high, okay, T low value, if that is high and T high value is low, okay, so in that case COP will be what? Higher. So if you are considering two seasons, one is summer season and other is winter season, okay, what will happen? Let me explain you this with the help of example. So if you are considering application as a refrigerator and this is the food cabinet, okay, this T-low, it is food cabinet, okay, this is food cabinet, and this T high, it is kitchen, okay, or surrounding. Now what is the in which case surrounding temperature is less, summer season or winter season? Okay, basically what we require is this T high value, it should be low, okay, this T high value should be low. Now surrounding temperature, it is low in which season? It is low in winter season. Okay, so if TH is low, from this formula we can conclude that if you are using a refrigerator or air conditioner, okay, the application is not a problem. If you are using refrigerator or air conditioner during winter season, COP will be more. Okay, now second concept we will see. Suppose in second example we are considering again this one, okay, and we are fixing the season. Okay, suppose for example we are considering summer season. Okay, summer season. Summer season means what? This T high value, it is fixed. Okay, this value is fixed. This value is fixed. Now in summer season, suppose we are changing the application. Okay, so suppose this T low temperature. Suppose there are two application. One is air conditioner and second one is refrigerator. Now, what is the temperature at which you operate the air conditioner? It is usually 24 degrees Celsius. Okay, for human comfort, we keep the temperature as 24 degrees Celsius. And if you consider refrigerator, what is the temperature of refrigerator? If you consider freezer, it is suppose minus 19 degrees Celsius, just for example. And if you are considering refrigerator part, where milk is kept, there suppose the temperature is 4 degrees Celsius. So for now we are considering refrigerator temperature as minus 19. Minus 19 degree Celsius. So out of the two applications, air conditioner and refrigerator, which T low value is maximum? You can clearly see air conditioner T low value is maximum. And from this formula, if T low is more, COP is more. And we are fixing this TH. This TH value has been fixed. Okay, this TH value is fixed. Why? Because we are considering only one season, summer season. So if you are considering summer season and if you are comparing between, so if you are considering summer season, meaning this T high is fixed. So you can only change T low and that T low will change based on application. If AC is there, T low is supposed 24. If refrigerator is there, for example, we are considering minus 19 degrees Celsius. So T low is more, in which case air conditioner. So COP of air conditioner will be more than COP of refrigerator during same season. Very important point, you should remember this. One more thing, okay, we'll just go back to the previous question which I had asked. Okay, suppose we are keeping application same. Okay, suppose we are cancelling this AC, we are just keeping refrigerator, but we are changing the, so we are fixing T low. Okay, so we are fixing T low when we are keeping the same application, but we are changing the surrounding. Okay, suppose we have summer season or winter season. So refrigerator will be having more COP when T high is less, and that is during winter season. So you should remember this point about the season. So if you're uh, checking season, keeping the changing the season and keeping the application same, winters in winter season COP will be highest. And if you are considering a particular season, either summer or winter season, and you are changing the device, either refrigerator or air conditioner, in that case air conditioner is having more COP.